Recall that in some cases, evaluating a trace at a Kaj-John-Lustig basis element is the same as evaluating an imminent at the path matrix of a simple zigzag network or descending star network. Now there's a couple imminents that we have nice forms for. One of them is the induced sign imminent. So let's look and see how we can use that to evaluate induced sign characters at Kaj-John-Lustig basis elements. Recall that for A, the path matrix of the zigzag network FW, W avoiding 3, 4, 1, 2, and 4, 2, 3, 1. We have that for any trace theta of the symmetric group, theta of the Kaj-John-Lustig basis element indexed by W equals the theta imminent of the path matrix. So let's see what happens in the special case that theta is an induced sign character. So let's say we have a partition lambda with our parts. And let's say we have a partition W in the symmetric group avoiding 3, 4, 1, 2, and 4, 2, 3, 1. We have that the induced sign character indexed by lambda applied to the Kaj-John-Lustig basis element CW equals the number of colorings of path families in FW such that lambda I paths have color I, for I equals 1 to R, and no two paths of the same color intersect. To see this, let's let A be the path family of FW. Sorry, the path matrix. Then epsilon lambda of the Kaj-John-Lustig basis element is the epsilon lambda imminent of A, which is the sum over all ordered set partitions of type lambda determinant of A I1 I1, determinant of A I2 I2, etc. So we have a product of R minors there. And each one of these factors in a term is, by Lindström's lemma, this is the number of path families from sources I1 to sinks I1 that don't touch each other. So we can think of this as color 1 path families and up to color R path families. So that's really all there is to it. So let's do an example. So let's find the 221 induced sign character of the Kaj-Town-Lustig basis element indexed by 34521. This is a 312 avoiding permutation because you can see after any letter we never see two smaller letters in increasing order. So this permutation avoids 312, and therefore it avoids 3412 and 4231. So there's a descending star network representing this. So we'll write this in two-line notation: 1, 2, 3, 4, 5, 3, 4, 5, 2, 1. 3 is a record, 4 is a record, 5 is a record. So we have a star from 1 to 3, and then 2 to 4, and then 3 to 5. And then when there's more than one spoke between two stars touching each other, we just replace them with one road. And if we wanted the reversal factorization here, we would put extra stars in between them. So we'd have this 3 star, 2 star, 3 star, 2 star, 3 star. We don't need that right now, but that gives the reversal factorization of this permutation. Alright, so we're going to have 2 paths of one color, 2 paths of another color, and 1 path of a third color. Now because of paths sharing edges here, it might be slightly hard to see which paths can possibly be colored the same. So let's summarize path relationships with a poset. Let's call it P of FW. This is FW here. So 1 is touching 2, it's touching 3. Touches both of them here. It doesn't touch 4. 4 goes here and then down and then up, but doesn't touch 1. 2 touches 4 right here, and 3 touches 4 right there. So those two are not less than 4, but 1 is. 5 doesn't touch 1. 5 only goes down to here, and 2 only goes up to there. So 2 can go below 5 also. 3 cannot go below 5 because it touches 5 right there. So I guess this is it. This is our poset telling how the paths are related. So let's see, so we have color 1, 2, 3, so we could choose either one of these 2-element chains in the poset to be a path family of 2 paths of color 1. I guess 1, 5 couldn't really be the path, the pair of color 1, because then 2 and 4 we couldn't color. Well, it wouldn't be a. They intersect. 2 and 4 intersect, so they couldn't be the same color. So we can have 1 and 4 and 2 and 5, and then path 3 is going to be color 3. Or 2 and 5 could be color 1, 1 and 4 could be color 2, and 3 could be color 3. So those are the only 2 options. So it looks like our evaluation 3, 4, 5, 2, 1 is 2 because of these 2 colorings. And actually, we can think of these colorings as tableau. So column strict tableau, except that I guess when we said column strict in the past, we meant that one number had to be less than the number above it. So here, even though 2 is less than 4 as integers, we wouldn't want them in the same column because they're not 2 paths that could get the same color because they intersect. So let's say column strict p tableau. So the difference between a tableau and a p-tableau is that in a p-tableau, we're looking at less than, greater than, etc. in terms of the poset, not in terms of the integers. So the poset P of FW is defined by I less than J in PFW. If I is less than J as integers, and path pi I is entirely below path pi j. Here, pi 1 through pi n is the unique path family of type E in FW. And column strict P tableau is an arrangement of poset elements into a tableau. Column strict means where if we have I below j, that means that I has to be less than j in the poset. If we just say P tableau, it's an arrangement of poset elements into a Young diagram with no restrictions on what can be in the same row or what can be in the same column. So we can restate the claim in terms of P tableau as follows. So if we have W and Sn avoiding 3, 4, 1, 2, and 4, 2, 3, 1, then epsilon lambda of CW equals the number of column strict P of FW tableau of shape lambda transpose. Because each column is going to be a chain in the poset of size lambda. And that leads to another proposition. So let's let W and Sn again avoid 3, 4, 1, 2, and 4, 2, 3, 1. Then there's another permutation in Sn avoiding 3, 1, 2. So this is a subclass of that class, a smaller class. And that other permutation V has the property that for all traces theta, we have theta evaluated at CW equals theta evaluated at CV. So if we know how to evaluate a trace at all 3, 1, 2 avoiding permutations, then we know how to evaluate it at all 3, 4, 1, 2, 4, 2, 3, 1 avoiding permutations, as long as we can figure out what V is based on W. And the proof is that if we look at the path posets of permutations avoiding these patterns and the path posets of permutations avoiding these patterns are the same. So we claim that there exists V avoiding 3, 1, 2 with the path poset of the descending star network corresponding to V isomorphic to the path poset of the zigzag network representing W. Now this would be a little tedious to write out in full detail, but I think the idea that I'm going to give you is pretty convincing. So let's say we have, I'll just draw a zigzag network here. So let's say these are the x's in a zigzag network, and where there's two paths between two stars, I'm going to erase the two paths and just leave them with one road. So this is for W. And then at this star, I'm going to flip everything across a vertical line and get a descending star network. I think I put in all the edges there. So just flipping on this vertical line. And then if there were another zig here, when that gets flipped, then I could draw another vertical line and flip, flip, and sort of just unfold this zigzag network until we get a descending star network. Now you can see that if a path the path here is less than some other path, then its mirror image is also going to be left, because when we unfold and do this mirror image, we're not creating any new intersections before paths or removing any intersections between paths. We're just writing the paths backwards. And the intersections between paths stay exactly the same. So this is for V. And this one is W avoids 3, 4, 1, 2, and 4, 2, 3, 1. And V, because we get a descending star network, avoids 3, 1, 2. Now, since this trace evaluation just depends on the poset, and these two permutations correspond to the same poset, then we get our result. So we unfold the zigzag network into a descending star network. So now epsilon lambda of the Kaj-Johnlistic basis element indexed by W equals the number of column strict PFW tableau of shape lambda transpose. And since PFW is isomorphic to PFV, that's equal to the number of column strict PFV tableau of shape lambda transpose. And that's equal to epsilon lambda of CV. So the induced sign character evaluations are exactly the same. Now, induced sign characters form a basis of the trace space. So now if we have any trace theta, let's write it in terms of the induced sign character basis as the sum of, let's say, A lambda, epsilon lambda. So theta equals that. Then theta of CW equals a sum of A lambda epsilon lambda of CW. Now epsilon lambda CW is the same as epsilon lambda CV. But this linear combination A lambda epsilon lambda of traces is just equal to theta. So with this unfolding algorithm, we really only need to be able to compute, we only need to be able to evaluate traces at the 312 avoiding Kaj-Johnlistic basis elements indexed by 312 avoiding permutations in order to evaluate them at all Kaj-Johnlistic basis elements for permutations avoiding 3412 and 4231. The end.